Good morning, mathematicians. How we all doing today? Time for more spectral sequences. Yes. Yes, indeed. Yes. Yes, indeed. Yes. Yes, indeed. Yes. Yes, indeed. Spectral. 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 Spectral sequences. Do you guys like that little diddly? It's for my upcoming album. Yes, indeed. Called the E2 page. There'll be a whole bunch of albums with subsequent pages. Unless it converges on the E2 page. Unless I do, what's his name? Sufjan Stevens. Be like, I'm going to write an album for every state. And then that didn't last very long. What an insanely overambitious goal to state out loud. Like, how many people in history have even made 51 albums? How many states are there? Crazy stuff. Okay. Anyways, let's do some math. In the section, notion of classifying spaces, group cohomology will be reviewed. These are theories necessary to get into Lyndon-Hochschild-Serre spectral sequence, and it is applications. The applications of our sequence. Let's get this guy ready. 8 states? Wow. It looks like so much more when you're looking at the map. Okay, what do we got? Topological group. We've got G actions. We've got principal G bundle. Definitely typo. This should be a P, or that P should be an E. When GX trivially on B? Is that a G bundle? Yeah, I guess so. Spectral sequences sparks joy. Spectral theorem does not spark joy. I don't know. I think the spectral theorem's cool. I think the spectral theorem's cool. Maybe after this document, we'll try and find a way to prove the spectral theorem with spectral sequences. How about that? I really got to buy a less squeaky chair. But, like, I'm going to be here less than a year. So, you know, do I really want to buy? Do I really want to go through the trouble of buying a less squeaky chair? Okay. B has a covering of open sets, right? So G equivariant morphism, sure. Yeah, right G actions. Why are we doing right G actions? That's gross. Okay. Good morning, Mom. Principal G bundle is your street name, Boris? Good to know. You're the one I've been hearing about. I'm always worried I'll get demonetized if I say these words out loud too early in stream. With all the spectral theorems, good. We need well-rounded individuals here, Leo. No cursing in front of Kay's mom. Well, I mean, I curse in front of my mom sometimes. Does that make me a bad son? I don't know. Mom, I don't curse too much in front of you, do I? Only just to give you a hard time. Do I believe in the lone genius trope? No. I mean, well, what? Yeah. No. Yeah, well, my mom's cool. She knows how to curse, so. Hello, Kastaka Kori. Given a principal G bundle, just a little, but usually no. Okay, cool. Cool. What about the lone idiot trope? Yeah, that I believe in. This is not Lee theory. Oh, Mom, I was responding to other comments here in chat. I was responding to other comments in chat. My mom is pretty liberal if she allows cursing. Yeah, I suppose she is. Also, I mean, at this point, I'm a 33-year-old man, so, if my mom doesn't really make sense to talk about her allowing or disallowing things. Oh, Mom, there's more people in chat asking me to try and teach you math in a video, so maybe when I'm home for Christmas. Your mom enforces cursing in almost every sentence. Well, we've got a whole spectrum of attitudes here then today. I don't look a day over 40. Yes, only about some things. My mom is liberal, she says. And I am an adult, that's true. I am a big boy now. Yeah. It would be a comedy. I think that's partly why people come here to my channel. It's for the comedy. Okay. So we've got principal G bundles. We can form pullbacks of our principal G bundles. Topological space. Let B be a topological space and P a principal G bundle over B. Suppose that X is a CW complex. And we have a pair of homotopic maps into B. Then the pullbacks are isomorphic as principal G bundles. Okay. Pulling back to CW complexes gives... you don't support humor, giggles, gaffes, or joy? What about guffaws? Or what about... what about having a gas? Would you support having a gas? What about having a grand old time? Right. Here's a cool theorem. Here's one of those cool theorems that you hear about. You never see these guys, but you hear about them. These cool theorems. The principal G bundles. If P is contractible. If P is contractible and XB is the set of homotopy classes of maps from X to B, and PGX is the set of principal bundles up to isomorphism, then the map by pullback is a bijection. Guffaws are okay. Having a gas is on thin ice. Okay, that's all I needed here. I just needed something. Your professor told your class that principal bundles are studied in geometric invariant theory. Wonder what kind of direction this is in the full algebra picture. I'm not totally sure I understand the question. I don't know a lot about geometric invariant theory, but I don't know, fixed points of stuff to do with algebraic groups, so makes sense that these are everywhere. It's true, principal GLN bundles are n-dimensional vector bundles. That is absolutely correct. B can be taken, moreover, B can be taken to be a CW complex. Okay. B is unique up to canonical homotopy equivalence. What does canonical mean here? Dangerous word. Playing with dangerous words here. And P is unique up to G homotopy equivalence. We call B a classifying space and P a universal bundle. For this theory to be of any use, we need to know that these exist, and they do. For any topological group. To see this, the transition data is exactly the same. Indeed. Yeah, at some point I'll get back to making videos about vector bundles. Am I a canonical sun? What do you mean by that? Recall that a map of topological spaces is called a fibration. A map of topological spaces is called a fibration. Right, if we have the homotopy lifting property. Let's just go back to this. Do I have canonical fun? Is all the fun I have natural? Or is there a standard choice of fun? Of course, mathematics. That's the canonical choice of fun. Right, but now we've got this G here, because I guess somehow we want it to be a G homotopy. This means that any homotopy with specified initial condition can be lifted. In particular, if B is path connected, then the fiber does not depend. Huh? Oh, up to homotopy. Sure. I call that the fiber. Sure. Okay. Fun exists, yes, but the proof is non-constructive. Is there a reference book that talks all the possible bundle theory that might appear anywhere in math? Well, probably not, right? I mean, there's a lot of papers and a lot of things about bundles. But I mean, if you just pick up random standard references on principal bundles and vector bundles, I mean, I'm sure you'll learn a good swath of what you need to know. So right now we're showing G bundles are co-representable. Are we? I haven't read that yet. Studying math is better than doing math homework. In particular, right. If this is a principal G bundle, it's got fiber G. The main relation that we concern between principal G bundles and fibrations is given by the following result. An admissible subgroup of G? What do you mean? What do you mean? Such that the induced action of H on there makes it a principal bundle. Okay. Then there is a fibration induced by the inclusion. Interesting. So BH we should think of as being bigger than BG. Okay. Whatever. And it's got fiber G mod H. Wait a second. Really? BH to BG? Okay. With fiber G mod H up to weak equivalence. Okay. I feel like the right way to think about various bundles is like a continuous map from the base space into spaces. Right. I mean, that's kind of there's like these two views on like the growth and deque construction, right? Where one is you view like a category, a fibered category, like you can either view it as like a fibered category. So say you have some, functor with some lifting properties, or it can be viewed as a pseudo functor S, and really it should be S into some category of spaces in which E lives, something like that, right? I could do a live stream series on homotopy type theory next summer. Maybe. I already have a video called Hot Boy Summer that I made about homotopy type theory. But you're right, I could do that. Odds are I'm not going to do it, though, to be honest. Well, it depends what happens. If I end up going to industry and getting an industry job, then maybe that's something I would do. If, however, I do a postdoc, then probably I will be focusing most of my time making, at least in the live streams, making videos, teaching myself stuff that will be useful to work under whoever my supervisor is going to be. Locally being like F cross B is basically being locally constant. Sure. Okay. Moreover, the inclusion of the fiber classifies the principal H bundle. I feel like I want to write some of this down. So we've got, if H is a subgroup, then we've basically got G down to here is a principal H bundle. And then also BH to BG is a fibration. we go. BHBG is a fibration with fiber G mod B up to weak equivalence, and right. And so if we pull back the fiber map, this corresponds to this bundle. Okay. In the industry job, wouldn't it be Excel Boy evenings instead? Maybe. I mean, yeah, depending on the industry job, I would maybe, I maybe would end up, talking more about some applied math on this channel. I don't see myself ever giving up the abstract math completely. You have nothing productive to offer, but these BG are related to nerves, right? Yes, that's true. Is homotopy type theory useful for homotopy theory chromatic stuff? Well, I'm not the right person to ask. You don't believe homotopy type theory would learn that much with homotopy theory? Well, yes and no, right? I mean, there's certain things, like one of the things that homotopy type theory excels at, it's a good way for having a synthetic version of homotopy theory, which is to say, you're doing homotopy theory in sort of an axiomatic way. And so, for example, like I remember in the summer school I went to, I don't think I talked about the proof in my video, but there's this really nice proof where you talk about, some qualifying things here. There's some sort of way that you're proving that the fundamental group of the circle is Z, right? And like when you first learn about algebraic topology and you're doing this properly, proving every theorem in detail in point set topology, like it takes a long time to actually prove that statement. But in homotopy type theory, well, I mean, it's sort of like cheating a little bit, because it's like we already know what the circle is, and so you sort of define the circle in a sort of homotopy type theory axiomatic kind of way. But then if you do it that way, then it's just like it's an immediate consequence of the definition, basically, because like you define the circle in homotopy type theory to basically be the thing that behaves like the circle in a homotopy like way. So, so all of that to say is yeah, I mean, I think there's a lot of work that you can do and is still done and needs to be done outside of homotopy type theory. But I wouldn't say that it's, I mean, again, I don't know much about this area. I wouldn't say that, oh yes, it's going to be very useful. I wouldn't say that it's not useful either, though. You know what I mean? Or category theory for homotopy theory, for that matter. Well, that I think is wrong, Leo. I mean, nowadays these things are indistinguishable. Like, what's the difference between higher category and homotopy theory in the modern day? I mean, yeah, okay, you could still go and like try and, I don't know, compute some homotopy group of a sphere in a very classical way, and I don't know, people would be impressed or something. But like, my impression is that nowadays, like, higher categories in homotopy theory are indistinguishable. Yeah, it's true. Maybe not as a first step to learning homotopy type theory, but I don't think it's that silly to learn some homotopy type theory alongside homotopy theory. The circle is defined circularly. Well, duh, it's a circle. Yeah, obviously. You're saying that category theory would be much more helpful. Oh, you're saying it would be more helpful. Yes. Yes. I mean, yeah. Yeah. I mean, to do homotopy theory or homotopy type theory, you need category theory. So, like, it's indispensable. Regardless. Okay, so if H is normal, then there is a fibration. BG to B of G mod H, given by the quotient map, with fiber BH. Sure. Let G be a topological group and BG its classifying space. We define the group cohomology. Nice. What a base way to define group cohomology. Friggin' based. Now we pass on to review some generalities about homological algebra. Yeah. Blah, blah, blah. Blah, blah, blah. Homological algebra, blah, blah, blah. ZG modules, blah, blah, blah. Yeah, we've got X and N. We've got a map. Also, you wouldn't say you're exactly a homotopy theory expert or anywhere close. Did a little reading of A1 homotopy theory like 5 years ago. Can I ELI 5 the notion of algebraic torus? So you're reading a paper which ended on some cool stuff on torus actions, but you don't know why it's cool. Yeah, actually, there's more. There's interesting things I need to remind myself about how tori work, because there's interesting stuff to say about split versus non-split tori and stuff. So maybe that's also something I want to come back and look at. But like, so yeah, a rep theorist should be able to on command say way more about tori than what I'm about to. I mean, the basic idea is that, well, what is a torus? What is a torus? I mean, as a group, this is C mod a lattice. Which is, I mean, it's what? It's S1 cross S1, right? This is sort of the first pass naive classical definition. Okay, how do I connect this to the multiplicative group? I mean, the point is your C mod a lattice. Hell yeah, baby. Yeah, actually, why would I I mean, what we're really interested in, this is also an elliptic curve over C, yeah. Maybe I should have a regular office hour soon and go remind myself stuff about tori. I mean, the point is like the basic example is like the complex numbers inside an algebraic group, right? Inside an algebraic group, we want inside an algebraic group, you know, it could be over any field really. We want some sort of example of, you know, It's just the diagonal matrices. So this is like the fundamental example of like, this is the torus in say GLN over some field, right? Well, when you finally ask me about the Lie theory stuff, among the questions is about maximal tori. Okay. Well, then I will, yeah, I'll be sure to review those things. Okay, let me answer some other questions in chat here for a second. I mean, this is the fundamental example. I don't know, Boris, maybe if this is already convincing to you that this is like a meaningful concept. But it's definitely something that, right? I mean, what could be more interesting than diagonal matrices, right? And diagonalizing matrices. So sorry, Hank Smith, before your question, how do I check myself when I learn new things? I have no idea. After these sequences, yeah, I don't know. How do I check myself? I don't know. I try to write a paper and see if it gets accepted. What do I think is my level of understanding? The idea of each proof level. Do you know the definitions level? Do you know 50% solutions? Like you're asking specifically about what's my understanding of spectral sequences right now? I don't know, not like amazing, but you know, if you had to, I now have seen enough examples, I could probably try and compute some examples fully on my own. And if what am I saying here? Yeah, if I needed to now do some spectral sequence or something computation for a paper, I mean, I'd still have to go look things up, but I feel more confident in my ability to do it now. Yeah, how much math do I do? How much math stuff do I do a week in hours? I have no idea. Yeah, I get asked this question all the time. I've been thinking about making a video where I answer frequently asked questions and just refer people to that. So I should start making a list. Maybe I'll start making a list. Maybe I'll start making a list. Desktop, new, note, frequently asked questions. How much math do I do a week in hours? I mean, it's a good question, but I have no idea, right? I'm thinking about math all the time, you know, and like last time someone asked me this question, it's like, okay, well, when I'm like walking to the bus stop and I'm thinking about math, like, does that count? I don't know. And like I definitely spend like an hour every morning live streaming, and then like several hours every week making a pre-recorded video, sometimes more. What do I like to do outside of math? I play piano. I have a piano. I like to run. I like to work out. There's other things I like too, but those are the main things recently, those are the main things that I do in my extra time. I spend most of my time doing math. That's the majority of my life is just doing math. And I play a little bit of piano, and I run, and I work out. That's, you know, that's life, baby. If the bus is late, it counts. Okay. Right, so what's this? This is just our cut product. We now start to explore those cohomology groups by identifying them in low degrees. Oh, by the way, I realized as looking into it, I was thinking about what do I do for 10,000 subs. I was thinking about doing like a marathon live stream, like 8 hours or something, and then making it like a charity fundraiser or something. And I saw that that actually you need one of the requirements to be able to do like a charity fundraiser live stream is to have 10,000 subs. So it actually works out nicely. So I've been thinking about doing that. So that'll be soon. I'm already at like, what, 9.4K? We now start to explore these cohomology groups by identifying them in low degrees and construct some particular resolutions. We define a mapping, right, sending every G to 1 and extended by linearity to the whole of ZG. Thus, the effect of epsilon on a general element, right, this is the augmentation map. Fundraising for padding Leo lectures pockets. Yeah, maybe not. Maybe not. What is this? Oh my god, what is this notation? Come on. I mean, I'm grateful for this note existing. Our friend, I forget his name, but yeah. This augmentation map, and it is a ring homomorphism. It is also a homomorphism of CG modules. And the kernel is this is the augmentation ideal. Two-sided ideal, because it's surjective. We can always use it to start a projective ZG resolution, and evidently Z is this quotient. If G is finite, we'll also consider the norm element. We're just not going to define the norm element. That's okay. I already know the norm element should be the sum over everything, right? It's just the sum of these. Do we normalize the norm element? Is there a 1 over G? I forget. Did a whole Galois did a whole series on Galois cohomology. I don't even remember if we normalize the norm element. No, we don't. Or the norm map. Right, the norm map. Right, it should be, we should go over all of these. Squid Game, but for grants. So just the real world as it already is, Boris. God knows you joined. You already have. Now we're cooking. I am a two-sided ideal. Wouldn't norm be product? Yeah, this is module stuff. This is module territory. That's a basis, fixed point set, cyclic group. We've got periodic homology. Yeah, maybe we should just write that down. We'll probably use those facts. Probably use these facts and logic. CNM H1 CNM kernel norm mod IG.M and H2G CNM isomorphic to H2 CNM isomorphic to M fixed points mod this. Classic stuff. I mean, we've seen this before. Emily Reel gave a nice general audience talk recently on formalism. Yes, I watched it when it came out. You're recommending it to all your non-lean-brained people. Most people here should be lean-brained already. How come there's no series on K-theory? Speaking of frequently asked questions, given the name of the channel, yeah. That's a good question, and I have no answer for you. Perhaps this is a sign I need to start writing the script. I need to start writing notes for such a series. Yeah, absolutely. Yeah. That's right. I've been exposed. But soon. I mean, I should probably finish. I've never finished my series on the truth about tensor products. But no one seems to care. No one's been, begging me to finish that series. Maybe I will at some point. But part of what I need to fill in anyways, I think the next video I need to make in that series is how to go from compatible local sections to global sections. You hope I come to the U.S. East Coast for a postdoc? Actually, I did apply to Maryland. So there is a non-zero probability of that happening, but that is only one of the various postdocs I've applied to. ICM next year in Philly. You've been thinking of making a video. I mean, if I do end up in Maryland, yeah, I don't know when the ICM is. If I do end up in Maryland, then maybe I'd go to Philly for the ICM. But I don't know. Am I that interested in going to the ICM otherwise? I don't know. Actually, maybe it's a good idea if I'm starting to take this channel a little bit more seriously. That'd be a good place to go and interview famous mathematicians and stuff. You've been thinking of making a video on every tensor product because people seem confused and you can just list them. Yeah. I mean, that was the point of making my video series, is I wanted to talk about, well, not every tensor product, but the, I wanted to explain the joke that a tensor is something that transforms like a tensor. And I wanted to explain what a mathematician thinks of when someone says tensor, what a physicist thinks of, and how they're related. Okay. So spectral sequences, we've been here before. This is the whole series. We're pros at this now. Let's jump to boom. I think we've even seen this one before. Following Leray construction due to Serre. Right. We have seen this one before. You cannot understand a word here? Well, maybe I got to make some... eventually, I'll also do more videos on basics of cohomology theory, and so maybe eventually you'll understand some words there. Let this at least be inspiration for you for some new words to go look up. So I've got a fiber map with base B... and then there's a first quadrant spectral sequence. I mean, this is... We've done computations with this already. We know this stuff. With this, and where... the cohomology of the total space is summing up over the E infinity page. It's your first year. Well, I mean, this gives you a view of what you have to look forward to if you end up being interested in algebra and homotopy theory. Boiled down a ton, you'd just say a tensor is a multilinear map. Yeah. Actually, that's maybe, you know, that's a version of the definition I actually ignored in my original series, because I was talking about the way that you build it up from the module as like a quotient. But that's actually probably a better definition, more in line with the physicist one, but oh well. All you know about the tensor product is the magical way to make a bilinear map into a linear map, and geometrically it stretches or shrinks the vector space or module. That's true. I mean, you should go look at Axler and then go look at Aloofy. That's my recommendation to you. One of the reasons people get confused is when people say A tensor B, they mean an element of A tensor B, the tensor product of two vector spaces. Yeah. Nothing special there. Nothing special where? Tensor products or what's on the screen? Okay, we got filtrations. Spectral sequence converging here. What time do we start today, gang? Does OBS tell me how long I've been recording for? It does. Okay. Probably gonna end it off soon. And in fact, let me turn to my calendar. Let's see, what do I gotta do? Putting things in my calendar. There we go. Oh, I need to edit that. Oh, lordy. There we go. Nice. Hello, Locke. Haven't seen you for a little bit. When you first saw the word fiber, you thought of a tree, which you should probably think of. If you see it horizontally, you can cut across all its fibers. But if you cut it vertically, it's a lot easier. Yeah, that's, you know, you should be thinking about that. I'm not an Axler hater. No, I don't hate it. I do think it's a little silly, the lack of determinant, and then people talk about it like it's some plus, like it's some advantage. I'm like, no. You know, and I guess the part of me that's all like category theory pilled is like, yeah, doing stuff without choosing bases is nice and natural or something. But also at the same time, it's like, it's just a useful concept. It's useful to know how to compute a determinant early on. So was waiting for the live stream, but it came out a bit late. Yes, that's true, it did. So you had to finish dinner while arguing with someone on Discord about relativity. Hell yeah. We love to see it. We love arguments here about relativity. Each complex, total complex, blah, 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 blah. What is this notation? What is this 2 here? What is going on, man? Okay. Anyways, let's skip all that. And we come to Lyndon-Hochschild-Serre spectral sequence. Let's write this down. And I guess tomorrow we will, maybe tomorrow we'll do applications of it. Normal subgroup. And what do you mean the extension? Why didn't you put a 1 over there? Oh, okay, whatever. First quadrant spectral sequence, natural in A with an isomorphism. Wait, a first quadrant? Oh, yeah, okay. E2PQ, HP, G mod N, HQ, NA, converging to HP plus Q, GA. Also, you've been busy with exam prep. Well, that's good. That's important. You should be focusing on your exams. Choosing a basis is good, actually. But there is a basis-free linear algebra too. Yes. Although you still might write a linear algebra textbook that is partially to do things differently than Axler. No. Determinant is cool. It gives rise to a short exact sequence of compact Lie groups. Yes, indeed. Yes, indeed. That's yes, indeed. Hoffman-Kunz? I don't know it, to be honest. Yeah, never heard of it. Today you learned the second type of vise on infinity. One is that an infinite number of $20 bills is worth more than an infinite number of $1 bills because Cantor said some are bigger. That does not sound right to me at all. That does not make any sense. I'll be honest with you. I don't think that's accurate. The other you learned today is that infinity leads to contradictions. No, it does not. Because the set of even numbers being equally large as the all naturals is simply too weird. That is not a contradiction. That is not a contradiction at all. No. So that is incorrect, Lockheed. You got to check yourself before you wreck yourself. Today you didn't learn anything. You've been doing homework for days. Well, that's learning. Could be talking about the density definition. Yeah. You're stating the two nonsensical views of infinity. Well, I agree with you there. Those were nonsensical views of infinity. Yeah. Okay, in this section, we're going to apply the Lyndon-Serre spectral sequence and the Lyndon-Serre-Hochschild spectral sequence to compute group cohomology of some groups. So what are we going to do? Cyclic groups with FP coefficients. Interesting. Assume that we can find a finite length resolution. I mean, we already know that we can, where each thing is a finitely generated permutation module. More precisely, since G has two subgroups, there exist finite sets In and Jn depending on n, such that this. What? Huh? Why? Why is that true? Because of some fixed point stuff? This is unclear to me. Yeah, doing homework is where all the learning actually happens, yeah. You see 1 G mod n works for me in regular group theory? Huh? Explains why you don't like doing homework. You have most of the draft script of a video on 7 different types of infinity in math. Nice. I've thought about doing similar things too, but like there's a lot of different forms of infinity in math beyond just cardinality. That is also true. Yeah. Okie dokie. I think I'm going to end things there, and we'll jump back into this confusion tomorrow. You mean there are at least countably infinitely many infinities? Just keep taking the power set? Yeah, but I think what Leo's talking about here is like there's infinite cardinals, there's infinite limits, there's infinite ordinals, there's sets of, infinite measure. These are all different kinds of things, Yeah. Anywho, I'm going to go get some actual work done, although this kind of counts a little bit. So thank you all for joining me. Hopefully I'll see most of you tomorrow, and